everybody. Our director, Dr. Lisa Story-Lombardi, was supposed to be here tonight to welcome you, and she is detained. So I am going to tell you a little bit about our observatory, and I'm going to introduce Joseph. That's it. So we are the Las Cumbres Observatory. We are headquartered in Goleta, in the industrial park behind Raytheon. We are a full-service observatory. We're very small, maybe 30 people here in Goleta and 5 around the world. We have scientists, we have administrators, we have technical engineers, we have a software team, and we have graduate students. We are also a telescope factory. We actually build telescopes in Goleta. So any of you who come on a tour, you're going to get to see that. Currently, we have 25 telescopes that we operate around the world, roughly 34 degrees north and 34 degrees south, in a ring around the world. We have 3 apertures. We have 2 telescopes that have 2-meter mirrors in them. We have, I don't know how many that have 1-meter mirrors in them. Those are used primarily for science. And then we have a smaller network of 11 40-centimeter or 16-inch telescopes that are used for educational outreach and for some science. So our mission statement is to advance the understanding of the world, of the universe, through science and education with our unique global telescope network. How unique are we? We are the primary follow-up organization for time domain astronomy. Time domain astronomy is anything in the sky that changes. If there is something that appears one night that was not there the night before, that requires follow-up. We want to know what it is. So our telescopes can be trained on that object very quickly. They can follow it for days, weeks, months, years, if necessary, and we can characterize it for the scientists who need that data. You will be hearing more about this in the news, but as a follow-up facility, we work closely with other observatories. For example, gravitational wave observatories are about to restart an observing run. LIGO, Virgo are the ones you've probably heard of because they've been up and running and they're here in the United States. And Cumbres, which I believe is Japanese. And they coordinate their observations and share the data with us. So the most public and well-known discovery that we're known for is characterizing the kilonova that happened in August of 2017. This was an event that showed up on the gravitational wave observatories, and it had an optical counterpart. So we were able to identify it and follow it for several days. We were the only observatory in the world that saw the light intensity actually grow. That's that bump in the beginning of that graph, and then decay over days. A change in color also indicates the change in the quality of the light that we were following. And the locations on those Earths show you which of our telescopes were making that observation on that particular day. So as the Earth turns, our telescopes hand off observations to the next set. There's always a telescope in the dark. So, other things that we're going to be following, the Vera Rubin Observatory is going to come online sometime next year, I think. Has an 8-meter mirror, 3.2 gigapixel camera. I believe it is the largest camera ever built, and it's been installed. It's going to survey the entire southern sky every other night, I believe. It expects to see millions of changes in the sky per night, millions per night. So this is going to be an unprecedented amount of astronomical data coming to the whole world. And so our software teams they want to get ahead of this problem. They've been working on ways to process the information and to get the valuable things to the scientists who need it. And so we will be coordinating with them quite closely. We also do work in-house. We identify exoplanets. Those are planets that are orbiting stars other than our own. We call them exoplanets. And we do a lot of follow-up with the TESS mission, which is a project that belongs to NASA. So that goes on currently, and we have exoplanet scientists on our own staff. And we also have a solar system group that follows near-Earth objects. And again, we do follow-up for the NEOWISE spacecraft observatory, and Atlas. And there's going to be a new one going up in 2026. So this is our speaker tonight, Joseph Farah. He's wearing a suit tonight. Normally, he's in these UCSB t-shirts. He has many. So I'm going to read this and add my own little bits. So you're in for a rare treat tonight because he's the real thing. He's actually done this work himself, so he can talk about it with great depth and expertise. Currently, he is a second-year PhD student in astrophysics at UC Santa Barbara. He studies supernovae under the direction of our own Dr. Andy Howell. I'm going to make you stand up. He's in the audience. So as Joseph's doctoral advisor, and he's also adjunct professor, he teaches at UCSB, teaches astrophysics. Dr. Howell runs the Global Supernova Project, which is headquartered at LCO, and this involves hundreds of scientists around the world who study supernovae and coordinate their work. Joseph received his bachelor's degree in physics from the University of Massachusetts Boston in 2021. While he was there, he worked on the Event Horizon Telescope, that's the EHT that you'll be hearing about tonight. He was a Smithsonian Fellow at the Harvard-Smithsonian Center for Astrophysics under the supervision of Michael Johnson. He helped produce the very first image of the very first black hole, M87 star, and he led the development of novel techniques for analyzing and measuring the shadows of black holes observed with the EHT. He remains a member of the EHT collaboration, and he pioneered a method for dynamically imaging sources such as the galactic center on short timescales as part of the effort to image the black hole Sag-A star. Sag-A star is the black hole at the center of our own galaxy, the Milky Way. For his work with the collaboration, mind you, he's very young, Joseph was named a Barry M. Goldwater Scholar, a co-recipient of the Breakthrough Prize in Fundamental Physics. The Breakthrough Prize is the one that is funded by all the tech wizards in Silicon Valley that competes with the Nobel Prize. So basically at the age of 22, he won the Nobel Prize.
The EHT won it, like it was given, I co-received it with the EHT collaboration, like it wasn't individually given to me, that would be insane.
He's a co-winner.
We're going to give you after that.
In 2021, he was awarded by the American Physical Society the Leroy Apgar Award, which is also a very big deal. Outside of his research, he is a digital artist. He does tremendous things with digital art. And for fun, he is a competitive quarter-mile drag racer that Anne can drive. Okay. So now I'm going to turn it over what lies within imaging the galactic center.
Thank you so much, everyone. It's such an honor and privilege to be here. I'm really excited to talk to you guys tonight. Thank you, Stan, for that amazing introduction, and thank you, Sharani and SBAU and the museum for letting me come here and talk to you guys tonight. Hopefully, not bore you guys. So my name is Joseph. I'm speaking today on behalf of the LCO and the EHT, and normally I would say something like, today I'd like to tell you about the second image of a black hole. But I actually have a better idea. Today, I want us all to be black hole hunters. So join me as we leave the museum, and we're going to travel to one of the real EHT telescopes in the array. So say goodbye to the museum. We'll take a quick hop and a skip to the Santa Barbara airport. Where are we going? We're going to set sail for the Puebla International Airport in the beautiful country of Mexico. And, oh, Jesus Christ, that's $700 for a ticket. I don't think I can pay for everyone. Is it okay if I just mark you guys as checked luggage? So we're going to fly down to Mexico. We're now in Puebla. And we start on our 3-hour road trip from Puebla to one of the telescopes in the Event Horizon Telescope Network, which is a beast called the Large Millimeter Telescope, or LMT. We're going to drive past lots of scraggy grass and mountains. Sorry. That was not intentional. We're going to drive past lots of scraggy grass and mountains and desert, and some insanely beautiful views on our way to the telescope. I mean, just look at this thing. It absolutely defies logic. It is the largest movable telescope dish in the world. It's over 50 meters in diameter. So it's a little tough to visualize the scale of this thing. So I'm gonna help you out a bit, okay? So here is a picture of one of my collaborators took. And that is one of us nerds for scale. Look how big it is. You can probably see us right now looking at it from here. And this is just one of the telescopes in the EHT. All right, so we're gonna go into that. We had a long trip. We like everything to be working properly for the observation tonight, but we run into a little problem, which is that our atomic clock is broken. So this machine here inside the telescope is a special type of clock called a hydrogen maser clock. It keeps time for all the telescopes in the array. And it's very, very precise. So while your wristwatch might lose a second every year or so, this bad boy will lose a second once every few million years. They're very expensive too. So for all the atomic clocks in our array, it is over $2 million, 20,000 smackaroos for just this one. Funny story for another time, but I actually almost broke one of these. It was in a big box. I put my backpack right on it, and I got yelled at. So these things need to stay cold in order to function properly, but like really, really cold. But the cooling system in this one is broken, probably because some idiot put their backpack on it while it was in a delicate state of shipping. So what we did, the observation starts in a few minutes. The nearest engineer who can fix it is a few hours away. So I'll tell you what we do. I tell you what we did. In spectacular physicist fashion, we taped a door open to let the clock cool down, leading to this fantastic quote from a documentary about the image. This piece of tape should hold the door open long enough for the observation to run correctly. If it doesn't, the whole experiment could fail. And that really sums up the whole EHT for you. All the careful design, the decades of planning, centuries of physics. And a lot of the success of the project came down to luck and sacrificing an intern to the heathen gods for clear skies. Okay, but once everything's working, the observation can begin, right? The sky darkens, the telescopes come to life, and this is what they see, our beautiful galaxy. And they're looking in the constellation Sagittarius, at the heart of the Milky Way. And this region is occluded and clouded by the optically thick interstellar dust that lies between us and the center of the galaxy. Now, if you zoom in with radio waves, a whole new world emerges, bubbling and boiling with activity, as seen as in this 3mm image from the Meerkat telescope in South Africa. And if you zoom in even further, a very fascinating sight becomes clear. A set of stars that seem to move in incredibly eccentric and bizarre orbits. Isn't that wild? Like, these are stars many times the mass of our sun, and they're just flinging around. And if we track them for decades, one thing becomes very clear. These stars are orbiting something massive, powerful, mysterious, and invisible. Yes, sir. Oh, sorry.
Sorry, brief interruption. We're just going to share a screen.
Yeah, you
Okay, there we go. And let's bring that.
I can share that.
Yes, we want to.
Oh, yeah.
I want to bring it up first before we do that.
Well, you just come here. The story about me almost breaking an atomic clock is true. I did not make that up for giggles. I am genuinely not a clever person.
We're also recording this for people on Zoom. It's a dual lecture, so thanks for your patience, everyone who's here in person. The people at home couldn't see it, and now they can. So thank you.
So this thing that all the stars are orbiting is visible to everything except for the Event Horizon Telescope. For some reason, it's not clicking things. There we go. So the EHT is a special global interferometer composed of radio telescopes placed strategically all over the world. And it's tuned specifically to the unique 230 gigahertz radiation that the heated gas outside the black hole flings out. And it can ignore the occluding dust of the interstellar medium and zero in on its target, which is the murky shadow of Sagittarius star. It's a very special telescope for that reason. I guess I'm just going to play again. The EHT is a global telescope, and as a consequence, it has a global collaboration running it. So we really are global. We're composed of over 300 members from over 60 institutions in over 20 countries, working with an endowment of over $80 billion. And you're probably familiar with our most famous result, which is the first image of a black hole, the image of the supermassive black hole in the center of the M87 galaxy, 55 million light years away from Earth. This image is of a black hole that weighs 6 billion times more than our sun. So it's really, really cool. But it's actually worth taking a second to appreciate something, which is that image, which by the way is only 4 by 4 pixels, costs $80 million. And, that's not a great pixel to dollar ratio. You can get a black hole image from Dell with much better value. But it's only 16 pixels, but they're 16 very important pixels. And to understand why the image is so special, we need to understand something else that's really extreme about EHT, which is ridiculous resolution. So when we talk about resolution, we're generally talking about what's the smallest thing you can see. And so, for example, the human eye can see things on a scale of about 1 arc minute. And that's not going to mean anything to most people. So here's a credit card analogy. If you took a credit card and placed it about a football field away from you, that's about 1 arc minute. You wouldn't be able to see anything on the card, but you could tell I was holding up, your credit card that I stole from you. That's your average human eye, unaided by, glasses and stuff. But blah blah blah. So that's the human eye. Now, what about home telescopes? Right, that's kind of the next step up. A home telescope like this one that my girlfriend bought me for my birthday. No, she's great. I love her. So a telescope like this one can see about 60 times better than your human eye. So that's the equivalent of me being able to hold up that credit card from where I live in Goleta, and you guys being able to see it from where you're sitting right now. And that's just a home telescope. Space telescopes are in a whole other league. So while your home telescope has a resolution of about 1 arc second, a space telescope like Hubble, oh man, that stuff gets for real. So a Hubble Space Telescope can see 10 times better than your home telescope on a resolution of about 0.1 arc seconds, which is the equivalent of being able to see that credit card in LA from where you're sitting right now. And the JWST, it's actually not that big of a resolution bump, it's the same. JWST offers a lot of really other cool stuff that is not resolution related. But that's where space telescopes live. So now the question is, where does the EHT live? So we're working on 0.1 arc second scales now. Is it 0.01 arc seconds? Like 10 times better than that? Well, actually, we're gonna have to go on another trip. So we'll mosey on down to the Santa Barbara airport one more time. And this time, we're traveling to my family's home in Boston, Massachusetts. We're gonna take an 8-hour trip and fly 3,000 miles, drive to my house, and hold up the credit card, and the EHT could see it from where you're sitting right now. With a resolution of 20 micro arc seconds, it can see a donut on the moon, or an atom held at arm's width. Yeah, so it could see a credit card 3,000 miles away, but not just see the credit card, right? All the other stuff I'm saying, you just barely make out the credit card. The EHT could read the numbers off the credit card from where you're sitting, and use it to buy a non-janky hydrogen maser clock. I hope your credit limit's high. So suddenly these aren't just 16 pixels, right? They're the 16 most precise and highest resolution pixels in all of human history. So what can we learn from these pixels, right? Why are they so crucial to our understanding of the universe? So to understand this, we need to take a moment to understand the light that we're seeing, right? Why does this image look like a glowing donut? Or like Sauron's eye, or there's so many memes about what the image looks like. So the reality is we're not actually seeing the black hole, right? The black hole swallows in all the light that gets inside it, so we're not going to see anything from the black hole. But photons are emitted from the glowing gas around the black hole constantly. The gravitational pull of the black hole is so strong that it can change the direction the light itself is going. So if light is too close, it will just fall in, but if it's just outside the region of no return, the photons will get bent and twisted and eventually leave, resulting in us, the observers, seeing a glowing ring surrounding a patch of darkness. And this patch of darkness is called the shadow of the black hole. And since this shadow is a direct proxy for the gravitational strength of the black hole, we can use it to test general relativity, Einstein's theory for how gravity works on large scales. So, well, on all scales really. But, here's an example. So if the gravity, we have estimates of the mass of this black hole. And because we know how gravity works, supposedly according to general relativity, we can estimate how big the shadow would be. If the gravity is stronger than we expect, then it'll pull in photons from farther away. And you'll get something like an image on the right, where the shadow is a lot bigger than we thought. If the gravity is really weak, it'll only be able to pull in photons that are close by, and it'll get something more like the image on the left. But it turns out that the boring answer was the right one, which is that general relativity was correct, again, like it has been every single time for the last 100 years. But that's pretty cool, GR is right. So if GR is correct, what can we do with that? Well, we can look at these images and we can extract information from them. Information like the mass of the black hole, and how fast it's spinning, its angular momentum, and its inclination relative to us, so how it's tilted. And that's really interesting, but this is also where it gets really tricky, because black holes do have different properties. Just because M87, the first image, and Sagittarius Star, the image in the center of our galaxy, look very similar and are both supermassive, it doesn't mean they're both supermassive, if you know what I mean. So let's start with the black hole in the center of our galaxy. This is the image, spoiler alert. It's pretty big, right? 4 million solar masses and about 10,000 times smaller than what Ronnie said at the beginning of the talk. Sorry, Ronnie. That set me up for failure, man. Sorry. So 4 million solar masses. If you put it in the center of the solar system, the shadow would stretch past Mercury's orbit. That's how big it is, right? Big, right? But it's peanuts compared to M87. M87 is many, many times larger than Sagittarius star and our solar system, and has a whopping 6 billion solar masses crammed in there. So if you put the M87 shadow at the center of our solar system, that circle, that little, that little white circle, that's Pluto's orbit. That's the extent of our solar system. That white dot is Voyager 1, the farthest ever man-made anything ever. And we wouldn't even make it out of the little black thing that's like the fake shadow. So these things are really, really, really big. Now here's the issue. So even though these black holes look very similar, we're talking about two very different regimes here. So on the one hand, it would take light about 8 minutes to get from one side of Sagittarius star shadow to the other. More like 4 minutes, but 4 to 8 minutes. But for M87, it would take 4 days to do the same. So very different regimes with very different consequences. So M87 needs time to move stuff around because it's so large, right? It evolves really slowly. It makes it easy to take a picture of. Like taking a picture of a giant tortoise walking across a lovely meadow. You know, it's just gonna do its thing. You know, you just set up the camera, set up your lights, take your time. Like, it's not going anywhere. You're taking a picture of the turtle, not despite it. Meanwhile, the cocaine-addicted Sagittarius star can evolve and change completely in just a few minutes, making it more akin to desperately trying to take a picture of your hyperactive toddler pretending she is the Flash. Another good analogy to this, a surprisingly good analogy to this, is panoramas. You know when you take a panorama, but someone like moves and it results in a skewed image that does not reflect reality? That's actually surprisingly close, right? Cats aren't really this big. But if you didn't know what was going into making this image, you might think, for example, that horses are going into it. I love you guys. So yeah, it's a challenge with Sagittarius star because of how fast it evolves. But the thing is, we really want to make an accurate image of these things, especially in such a fast-moving environment. In such a fast-moving environment, we'd be able to see the black hole dragging space and time around with it. If we could get a high resolution of the image of the shadow, we could fit special shapes to it that would allow us to extract all of the information you could possibly think of from it. It's a really powerful probe into the most extreme environment in the universe. But this is a challenge to do for a number of reasons. And the challenges involved boil down to two big things: the variability of the source and the sparsity of the coverage. I'm going to explain what both of those are. So let's start with variability. So how variable is Sagittarius star? So in order to characterize Sagittarius star's variability, did you see the simulated data thing pop up for a second? That's a holdover from when I was not supposed to share the data. This is real data. So in order to characterize Sagittarius star's variability and determine if it would be a problem for our imaging, we have to zoom way out. And so we can look at the light curves captured by our most sensitive single stations, like the Atacama Large Millimeter Array, or ALMA. And we can observe fluctuations in the overall brightness of the source and use that to infer variability. So in essence, we're kind of like measuring the pulse of Sagittarius star. And just like how a rapidly beating heart indicates a human body in motion, from Sagittarius star's light curve, it can tell us how active the underlying black hole is. But it can be a little confusing to understand what's happening here. So let's start with the plot on the left. The plot on the left is showing how bright Sagittarius star is as a function of time. So on the y-axis we have brightness, and on the x-axis we have time, and Sagittarius star is getting dimmer and brighter and dimmer again. Very interesting. And so, but how can we actually use that to determine how variable the object is? Oh, sorry. Thanks. Apparently I'm going a little too fast. Sorry guys. I'm just very nervous, excited to be here. So how can we actually use this to determine how variable the object is? So the brightness is changing due to a physical process propagating across the black hole environment, which takes time. So a surprisingly good analogy is and you'll hear me say this a lot in this talk, is a Newton's cradle. So everyone's played with these, right? You pull one ball back, it knocks the other one. The force travels through the balls and knocks the other end ball flying in the air, and the cycle repeats. This is a really good analog for a chemical system. So a physical process is starting at one end of the Newton's cradle, or the black hole. It's propagating across the Newton's cradle, or the black hole environment, and it's causing the brightness to change. Or in Newton's cradle case, it's causing the ball at the other end to swing up and down. The smaller the system, the faster the process will move across it, right? You can imagine if you had, instead of 4 balls here, 5 balls here. And if you had, instead of 5 balls here, you had 50 or 500, it would take a lot longer for the force to get across because the force is traveling in finite time. So what if we like only restricted our view to just a cradle ball swinging up and down? If we track its motion, it'll look like it's oscillating. And the time scales that are associated with this oscillation are intuitively associated with the size of the system. So if we can, in this analog, if we can only see the brightness, we can use it to infer the distance a physical process would have to travel in order to change the brightness this quickly, and this gives us the size of our system. And if the system size is very small, in other words, big stuff is happening very quickly on small scales, the system is very variable, and that will make it very hard to image. So let's actually apply this to Sagittarius star. So we can get a characteristic frequency out of the light curve by looking at the power spectrum, and that basically tells us how fast is the heart beating. So let's assume the system is some object, it has size delta, and it's pulsing, right? You've seen this frequency change, this brightness change with frequency v. The ratio between the fastest speed something can travel, which is the speed of light, and the frequency that we observe gives us the maximum size of the object. If we actually calculate this, it turns out to be about 10 to the 12 meters, so 1 trillion meters, which sounds like a lot of meters, but it's actually only 22 times the size of the gravitational radius of the black hole. So only 22 times bigger than the black hole, and that's exactly the region we'll be imaging in. So all I've managed to convince you guys of is that this is going to be a tough thing to image. It's just going to be a lot harder than M87. And unfortunately, that's it. There's no magic here that's going to fix the variability for us. This is just, we have to characterize it and say, yep, this is going to be a problem. And that's why the first image came out in 3 years, and the second one took 5. Okay, so to understand why variability is a problem, though, we need to get into problem number 2, which is the sparsity of the interferometer. But before we even do that, we should probably ask, how does an interferometer actually work? So, all right, let's start with your basic telescope. The resolution of a telescope is determined by the wavelength of light that it observes at divided by the diameter of its collecting area. This is pretty intuitive, right? You get a bigger telescope, it's going to be able to see smaller things. But when you link 2 telescopes together via interferometry, their resolution no longer becomes a function of their individual collecting areas, it becomes a function of the distance between them. And so this is like a life hack, right? Because you can just take 2 tiny telescopes and place them on opposite ends of the globe, and you'll have an amazing resolution. But there's a catch. Of course, it can't be that easy. When you do this, execute this magic spell, the telescopes no longer see the image on the sky. They see something special called the Fourier transform. And now Fourier transform is this mathematical transformation. You give it an input function, like this square wave here, just goes straight up, down, and then the Fourier transform will tell you how to make this function out of a bunch of sines and cosines. And this is really convenient because light is a bunch of sines and cosines, it's a bunch of waves, and so this is a really convenient physical way to represent this kind of function. And so this is what the telescopes will see. But they won't see, a really important property of the Fourier transform is this. So if you take the Fourier transform of a function and you Fourier transform it again, you get the original function back out. And that's a really helpful property. It's called invertibility. Basically, yes, we're only seeing the Fourier transform of the object in the sky, but all we have to do is take the Fourier transform of it again, and we'll get the original image back out. So what if your image function is not a square wave, but a black hole, which, by the way, they're basically the same thing. It's a little unintuitive, but that's actually correct. The Fourier transform of a black hole image looks more like this. So it's like this ripple pattern called a Bessel function. And now, what does the interferometer actually see, right? This is like perfect. So if you took the image and just directly Fourier transformed it, it's not exactly what the telescope sees. The telescope sees this. So you have your 2 telescopes linked as an interferometer. They're connected by a vector called a baseline. And like all vectors, this baseline has magnitude and direction. And the 2 telescopes observe a combinatorial data product called a visibility. Now, the visibility that they observe corresponds to the point in the Fourier plane with that exact same magnitude and direction. So if you have many telescopes, each pair of telescopes forms a baseline with its own magnitude and direction. And together, they probe more of UV space. So the EHT has 8 stations observing for a whole night, and they produce this wonderful dot map of this sparse sampling of the Fourier transform. And that's what that means, by the way. So we're not covering much, right? Just what the white dots see. And that's the sparsity of the interferometer. But it is a really good way to get good resolution. So if you take the wavelength of light that we could observe at in 2017, absolute like bleeding edge, 1.3 millimeters of radio telescopes at the time, and you divide it by the diameter of the Earth, which is basically as far as we can possibly put 2 ground-based telescopes, you get 25 microarcsecond resolution, which is just enough to resolve the shadow of the largest black hole in the sky. And that's why the image is only 4 pixels by 4 pixels, because even this extreme resolution is just barely enough to actually see it. Okay, so we're back to the incomplete coverage problem, right? So the problem with the Fourier transform is you need all of this information, all the purple and yellow and black, in order to get the image out. But we only have what's in the white dots. So how do we solve this? And the solution is robust imaging. So robust imaging is all about inverting the Fourier transform. When you hear imaging a black hole, this is what this is actually referring to. Inverting the Fourier transform to get an image out. And this requires some assumptions which we try to minimize. And we minimize these assumptions, right? It has to require assumptions because you're taking information and then you're only sampling part of it and then you're trying to get all the information back out. So you need to make some assumptions. And there are different approaches that we use which make different assumptions. So the two main approaches that we use are called regularized maximum likelihood, really rolls right off the tongue, or RML, versus the clean iterative imaging approach. So clean is nice. It's an inverse modeling approach, extremely established and historical. It's been used for decades. And basically, it takes the Fourier transform and it says, okay, I'm going to assume everything I can't see is 0. And then it just inverts the Fourier transform and does an iterative procedure to clean up the image. And that sounds like a horrendous assumption, but it actually works very well. There's a problem with this procedure, though. It only gives you one solution. So if there are any statisticians in here, you'll know that if you have fewer data points than than the function can. If you have fewer data points than parameters in your function will be unconstrained, and so you can technically have infinite solutions. And that's the case for our images too. There are technically an infinite number of images that can fit the data, and clean only gives you one. So that could be it. It could be the wrong one. It could be the right one. And the other problem is these images can vary quite drastically depending on the expertise of the user. So this is a little alarming, but it's true. So you give two different clean experts the same data, and sometimes they'll produce different images because it's a very inherently a procedure you learn how to use and get good at. So the alternative is regularized maximum likelihood. So this is a forward modeling approach. Instead of taking your data and inverting it to get an image, it checks every possible image to see which one fits the data best. So this is a movie of the procedure actually running. So you can see it's like going through a bunch of images to try to see which ones fit the data best, and it's determining the fit based on those chi-squared values at the top. And it works extremely well. It also has another benefit, which is it provides a representative set of images, right? Because it's basically checking every possible image, so it can tell you, hey, here's what all the possible images look like. And if they all look the same, you can say, oh, my data is very good. If they don't look the same, you're like, oh, I guess I'm imaging my assumptions instead. Here's the problem though with RML. It requires some hefty assumptions. You have to bring in outside info in order for it to be more effective. And it relies a lot on your parameter choices. You can generally avoid this bias by being careful with your parameter choices, but the reality is if you choose the right parameters, you can make any image, including a picture of yourself, pop out of the imaging algorithm. So I've got a quick question for you guys. We actually tested that. That is true. I've got a quick question for you guys. Of these two approaches, which one do you think is better? RML. Hold up your hands if you think RML is better. All right, and clean. So that's interesting spread. So the actual answer is we use both approaches and then check them against each other. And they both gave the same result, which is a very good vote of confidence. It means we're insensitive to our approach, which is very good. But there was still a problem. So when we take test data that evolves like Sagittarius Star, this hotspot image on the hotspot movie on the left, and plug it into our imaging algorithms, we get really bad movies out. Believe it or not, that's a movie on the right. It's actually playing, but it's impossible to tell. See, that's like a legit movie. It's doing stuff. Kind of see that? But obviously, it's not representing the original synthetic data. So what's actually going on here? And to kind of get into the heart of what's going on, I'm going to use this visualization of our interferometer. So on the left, we have two baselines formed by a baseline formed by two sites, and they're measuring that blue dot in the Fourier transform. So that's the baseline, and you can see if you flip the x-axis, right, this line corresponds to this with the same angle and size, and then it produces a data point. And if we do this throughout the whole night, as more telescopes come into view, they probe more and more of the Fourier transform. Now this is fine if your source is stable over a whole night, but Sagittarius Star isn't. Sagittarius Star, in between these dots popping up, Sagittarius Star is changing. So we can only use subsets of the data at a time to produce an image. And that's a problem. So if we make a movie, for example, like a fake source like this is a static ring, okay? Nothing's changing in this movie. It's just a single static ring, and we produce a reconstruction of every single frame of the observation. This is what we get. A lot of garbage, and then very briefly, for a second, so a couple of good frames in a whole observation of LA garbage. Sorry. So we want to be able to pull those best frames out, but there's an issue, right? Anyone who's done data stuff knows that what I'm saying is setting off big red flags. You can't just pick the frames that you think look best, right? We don't know what Sagittarius star is supposed to look like. We could be picking the wrong frames for all we know. So can we predict where those good regions will be without needing to bias ourselves to the right answer? And the answer is actually yes. So the selective dynamical imaging method created this formula. You plug in your UV coverage into it, and it will tell you how good the reconstruction will be without ever needing to know what you're looking at. And this is really powerful because it means you're never biased. You're never biased with this method. You could literally run this procedure years before you ever took data, and it will be right every single time. So we're not worrying about we're not cherry picking the data. So if we apply to the Sagittarius star data, we basically see that there are clear regions where the score is higher than others, and that's where we expect the reconstruction to be the best. And if we image in those regions, we get much better results. So the method of selective dynamical imaging was basically how it made it possible to produce accurate images with very limited coverage, and it overhauled the imaging process for objects like Sagittarius star, and made it possible to produce the images that you've seen. Okay, so I've gone all into the imaging and the telescope and the horror stories. Let's talk about the image. Okay, what does it tell us? And I'm gonna need a drink.
I get very animated in this bit. I know, more animated?
Sorry. I can hear you guys thinking it. Okay, so you guys are a great audience. Seriously, I appreciate you guys laughing at my terrible dad jokes. So, what is this image? It's a second image of a black hole, ever. That, right there, mic drop moment, right? And it's the first image of the black hole in the center of the Milky Way galaxy. That's pretty cool, because up until this point, we weren't really sure there was a black hole in the first place. Then we were pretty sure, but there was always that 1% chance that GR was wrong and Einstein was a kook. And there's a ground star in the middle there. It's a big dark matter cluster. But no, it's a black hole. And it's a really beautiful looking black hole in my opinion. But so this is a really cool image because this is actually the first horizon level structure connection to the stellar orbits we saw earlier. So that's what that object is right there. That was swinging the stars around. That's the black hole. That's what's doing that stuff. And it makes sense, right? It was mind-blowing because those stars are many times more massive than our sun, but that black hole is 4 million times more massive than our sun. So it it checks out. So what else is this? All right, so this image is just like the M87 image is a test of general relativity, right? We can use the same thing. We can take a look at the size of the ring and confirm that it matches our expectations from general relativity. And we've confirmed once again that general relativity is, despite how boring it is, correct. But this is really powerful, right? Because now we have tests of general relativity that span 3 orders of magnitude of mass in a black hole. We've confirmed that a black hole, look how similar this image is to the M87 one. We've confirmed that black holes of millions of solar masses function exactly like black holes of billions of solar masses. And that's really, really interesting. It'd be like if you took a picture of the bacteria on your skin and they were dressing up and driving out and going to an astronomy talk on a Friday night. You'd be like, whoa, everything's functioning the same. So that's really, really interesting. And that's kind of like the really nitty-gritty about why this image is interesting. But there's also a much more higher level beautiful reason, which poor Sandy has heard about 10 times by now. This is a picture, and this is what it really means. This is what it means to me. This is kind of more of a, oh no.
Black hole. It'll come back. Give it a second.
Okay. I'm gonna keep talking.
Tell some jokes.
This is a picture of where physics breaks down. And that's kind of a weird concept to wrap your head around. So let me tell you a little story. In the last 100 years, there have been 2 major theories of physics that have been wildly successful. And there are people in this room that have worked on both of those theories. General relativity, right, describes really big, really massive things developed by Einstein in the early 1900s. And it's been tested again and again and again and again. And I can't tell you the level of this testing, right? The very first test was mind-boggling, right? Arthur Eddington, took pictures of stars before and after a solar eclipse to determine conclusively that the light was being bent by the sun's presence during the solar eclipse. And that was the first real test of general relativity. And then a few years later, they showed that GR could explain the precession of the mercurial orbit. The fact that it's not just moving like an ellipse, it's moving like a little flower. And so it's just passed tests again and again and again. Well, recently, it's passed the gravity probe B test, right? Where we use the weak gravitational field of the Earth to adjust a gyroscope in a satellite by a millionth of a hair, and that was enough to prove that GR was working around Earth. And then we went even bigger in scale, right? With LIGO detecting gravitational waves, two black holes colliding, millions of light years away, creating ripples in the fabric of space-time that flex the Earth and the whole Milky Way galaxy, the whole universe. And then there was the image, the first image of MD7, right? The first evidence of a horizon in the universe. A place, right? This is an image of a horizon, a place where nothing has ever come out of. Anything that goes into there stays there. It doesn't come back. It's a gateway or an exit. It has a deep philosophical, it asks a deep philosophical question, but it answers an even more important question, in my opinion, about general relativity, which is, horizons in the universe exist. So over and over and over again, general relativity has been proven correct. Again and again and again and again. Now there's a second theory called quantum mechanics. You've probably heard of it. Quantum mechanics also has been tested rigorously. It describes the very, very small and the very, very fast, things like photons and subatomic particles. And it has been tested over and over and over again for the last 100 years. And we've developed this beautiful thing called the Standard Model. And like general relativity, it's been proven correct again and again and again. And it's difficult to overstate how correct quantum mechanics has been, because it has predicted some weird stuff. And every time we thought, okay, this is too weird even for quantum mechanics, time to go to the quantum mall and get a new theory. Every time we thought that, it was like, oh no, actually, we were the wrong ones. We were interpreting the experiment wrong. Our conception was outdated. That's how right quantum mechanics has been. So these two unbreakable, never incorrect theories, right, one describes things that are very big and very heavy, and one describes things that are very small and very fast. And the problem is black holes are both big and heavy and small and fast, right? They're huge, 6 billion solar masses. This one's 4 million solar masses. That is massive by any definition, and we use general relativity to make all the predictions for this image. But it's also very, very small, right? It's all this mass is compressed into a point of infinite density, basically. So we can also technically use quantum mechanics to describe what's happening in here. And it's a perfect opportunity for our two perfect theories to go head to head, and we ask them what happens in the center of this thing. These two always correct theories that have never been wrong, the always correct ones, they give completely different answers. And that's severely problematic because, like, one of them has to be wrong, and if it's GR, that's a huge problem. If it's quantum mechanics, that's a really, really, really big problem. Like, I mean, everything that we know about physics, if we prove that one of these things was wrong, everything we know about physics would change drastically overnight. And we have a picture that says, yeah, things exist where one of those things is wrong. And we have no idea which. And it keeps me up at night in a good and a bad way. But it's the excitement, it's what, in my opinion, it's one of the most exciting questions in physics, which is, now we can't ignore this problem anymore. Before we'd say, what's a black hole anyway? Like, so you have one? Like, do you prove it? But now we can say, hey, here's a picture. Theorists, get cracking. Like, what's going on? And so that's really, really interesting to me. And so yeah, we can ask all these philosophical questions all day long. But we can also do, like your hardworking, everyday factory physicist stuff with this image, which includes drawing rulers on it and making measurements. So we can draw a ring on the image and find out that it's about 50-ish microarcseconds in size. We can measure the width, like a dentist checking your whatevers. And I'm not a dentist, I don't know tooth words. And we can take a look at these like hotspots, these blobs. Like, what are they? Are they friendly? Are they even real? There's a very good argument that these blobs might not actually be real. It might be a product of our imaging algorithms. So let's start with the ring size. So we have a ring size, 50 microarcseconds. We can plug this into a very simple formula that will tell us the mass of the black hole. And surprise, surprise, we were able to confirm pre-existing measurements and confirm that Sagittarius star has a black hole mass of 4 million solar masses. That is a lot of solar masses, but it lines up basically exactly what was predicted already from other experimental observations, except this is, of course, the most precise estimate of this mass. So what else can we do, right? We can take a look at this image, and we can compare it to a massive library of simulations. And this is really neat because we can look at the simulations and simulate observations with the EHT and say, hey, this simulation kind of looks like the black hole image. And so we can compare it, the best fitting simulation, to the black hole image and ask the computer, hey, what parameters did you use to generate this black hole? And it will tell us, hey, the black hole you've taken a picture of looks like the simulation I made where, and by I mean the computer, not me. The simulation, the computer made with a 30-degree inclination. So that means it's like kind of, you're not looking at it right down the barrel, which would be bad for our health. But you're also not looking at it like edge on, like interstellar style. It's also apparently a magnetically arrested disk. So that's really interesting because it means all the material around the black hole is caught in a magnetic field and it's kind of being dragged around as this very, very, very high energy object. It's like bending space and time with it. And the accretion matter has a prograde spin. So all the stuff that's swirling around the black hole, it turns out that it's moving in the same direction that the black hole itself is spinning. And that's not necessarily required. And so it's really interesting to see that, yet again, the black hole seems to have this property. And so we can measure these properties for all the black holes we can take images of, all 2 of them. And we can add them to our black hole zoo. And this will allow us to, build out these demographic surveys and ask and answer questions about, how black holes evolve and what kind of distributions they have in the universe. And this helps us answer questions about how the universe evolved and what its ultimate fate will be. Okay, so that's the Sagittarius starting stuff. So what's next, right? I'm getting through a lot of stuff here, but this is not a bygone result that I'm just talking about. This is real science that's happening right now. So what's next for the EHT? And the short answer is we're going to sharpen everything. So we're moving to Space VLBI. I'm actually participating in a conference later this month where we will be designing the mission parameters for a Space VLBI concept. So why are we going to space, and what does Space VLBI mean? Basically, right, you have the concept where you take 2 telescopes, you place them further and further apart, it gives you better and better interferometric resolution. And that's really exciting, but there's a limit on how much you can put those telescopes apart, because the Earth is only so big. I wish it would be bigger, but them's the cards. I don't make the rules. So an easier solution, easier than making the Earth bigger, is to go to space. So we have lots of space telescopes in there already, but this is really challenging for the EHT. So a space telescope is already a really, really hard thing to do. But the EHT, each station in the EHT has to know exactly where it is in the universe. That's why we need these crazy atomic clocks and these unbelievably precise global positioning systems, because the telescopes have to know the exact distance to each other in wavelengths of light. Like that's how we measure. When you look at those plots of like the Fourier transform, the x-axis is measured in number of wavelengths of light. So like we measure the distance from the Greenland telescope and the South Pole telescope is like 10 billion wavelengths of light, and it's at the wavelength we observe at. And so you have to know your location on the Earth to within that number of wavelengths of light. And it's a very difficult challenge, made even more challenging by having to do it in space, where nobody knows exactly where you are down to that kind of precision. In fact, our telescopes, the ground telescopes, are so precise that the United States Geological Survey uses them to measure continental drift, because they know their distances to each other so well, they can measure the continents drifting apart, because they can see the distance to each other changing. And that's pretty cool, but again, really challenging to do in space. But if we can go out to longer baselines, we'll have much better resolution. So, for example, we partnered with NASA very recently to potentially put a radio telescope 1 meter on the International Space Station, or even one on the Origin Space Telescope, which will be going out to join JWST sometime in the next 1 to 2 centuries. Man, there are a lot of people who know about the Origins delays. But yeah, so that would be amazing, right? You'd have a 1 million mile long baseline, and you can't imagine the science we could do with just 1 million mile long baseline. With just a single 1 million mile long baseline, you can measure like basically every black hole you can think of and immediately probe its mass and spin, like which is literally a couple data points. It's that incredible. Aside from that, though, right? Because as much as I'd like to, I can't just shoot a satellite into space. That's going to take probably decades. So what's next? Well, we're not stopping there. We're also upgrading the entire EHT ground array. So we're adding more telescopes, which gives us more spatial density. So ideally, right, the ideal scenario would be the whole Earth is just covered in telescopes, and that's a personal fantasy. That may not be shared by everybody. But that would be the ideal case for the EHT. But we're doing the next best thing, which is putting telescopes in as many places as we can. Like we've got a new telescope that we're developing in Africa. We're putting telescopes in hopefully in China, shopping malls, movie theaters, bolted to the roof of your house. You get tax credits if you let us put a telescope in there. So that'll be great. But also, we're improving the frequency of these telescopes. So all the stuff that I've shown you, these images are made at 230 gigahertz, which is radio wavelengths. But recently, when I say recently, I mean literally last month, we just tested an observation where about half of our telescopes were online for 345 gigahertz. And from a technical perspective, the observation was a smashing success. From a realistic perspective, the weather sucked. So we did not get good data. But we are working on upgrading the resolution of these telescopes. So 345 gigahertz from 230 to 345, instantly 50% better resolution. So those images that you saw will be getting a lot sharper coming very soon. That's like the space Milky Way stuff. That's like kind of longer term, but this stuff is like happening right now. Like in the next couple of years, you can expect to see really exciting new measurements. Also, and this is partially space Milky Way, partially ground-based, but we like more frequent time sampling. So we've been making images so far, but if you had an orbiter that was orbiting Earth every 90 minutes instead of having to wait 12 hours for the Earth to like kind of slowly turn itself around, you could make movies of black holes. And like, that's the coolest thing I've ever heard in my life. And that's like a area of very personal interest for me. So I mean, the selective dynamical imaging method is basically my unwritten love letter to making black hole movies possible. And so I think that's going to be coming up really soon, and I'm very personally excited about that. So I made this janky graphic to kind of put the future of VLBI into perspective for you. So this is where we are now. Images like this, blurry at best. We got a lot of comments when we like post, when we share our results from people who are like, they're very sweet, very kind-hearted people who just want the best for the science and the results. And like, it's really cool, guys. You did such a great job. But like, next time, play with the focus a little bit. Just a little bit, They're like, Canons have an autofocus feature. And we're like, we didn't think of that. We'll definitely make sure to do that next time. So we're currently at this stage, right? We're on the ground-based section of the book. We can only see a couple marbles, which I've creatively used to represent black holes here. And I forgot I animated the arrow points of the marbles. I forgot that a little bit too late. But so in the future, though, once we move to space, we'll be able to see like literally 1,000 times more black holes than we currently can, because there are plenty of black holes in the sky, but they're just really, really small. Or they're big, but they're very far away. And so once we get better resolution, we can see smaller things, we'll be able to see more of these black holes. But more importantly, the current images we do have will get a lot better. So when we go to Space LBI, instead of these images being super blurry, we'll be able to make these beautiful, like precise images of the black hole's photon rings. And that's the shadow bit of the black hole that will tell us all the good information. That's like the innermost stable circular orbit where photons are orbiting many times before they escape. That's the really interesting bit. So there's all sorts of really interesting stuff on the horizon for this. This is just truly just the beginning of what we can do with Space VLBI and the EHT. So I just want to say thank you so much to everyone for listening and to the SBAU for inviting me to do this talk. It's genuinely a privilege.